Good morning, everyone. My name is Lloyd Trinish from IBM. I'm an environmental scientist. I work at our labs in upstate New York. And I'm going to tell you at least a little bit about some of the challenges and issues around climate and climate science. Because to be honest, we as a species, we're at a tipping point. As you may have heard, we've hit 400 parts per million on carbon dioxide in the atmosphere. And this is unprecedented. The last time a level like that was reached was about 3 million years ago. And at that time, the average global temperature and the height of the oceans was much higher than it is today. So there's a bit of a mismatch. And as an aspect of this is we continue to study the science. And the science has actually been fairly well established for quite some time. And concerning the influence of CO2 into the atmosphere. And I've been involved in studies along these lines for a long time. And an aspect of this is, in the 1980s, I worked for NASA on climate-related topics. And what's interesting is that what we knew then is essentially what we know now. But the big difference is today is that we have much better precision about the information. We also have quantified and reduced the uncertainty. And we understand more about the impacts that we didn't understand decades ago. So, what does this all mean? When we think about the increasing in temperature associated with carbon emissions, although the emissions themselves are slowing, we are unfortunately on a path of reaching a 2 degree increase, that's 2 degrees Celsius increase in the next 2 decades. And that's a bit alarming. It's also, you might want to ask a little bit of sort of why that is true. Well, let me add a few more facts to this. The global average temperature has increased by a degree in the last century. And that's unprecedented in modern civilization for as long as we've had recorded measurements. And, but then there's also other aspects. So we want to look at the increase in the height of the sea level. So this chart shows this as a global average. And over the last century, it's increased about by 7 or 8 inches. But it's also accelerating. And the chart shows as we go into the future, that shaded area shows the range of potential scenarios associated with sea level rise. But what that also indicates is that by the end of the century, the sea level rise may be several feet. And that's something that we need to understand the impacts of that. It's more than just seeing polar bears sitting on ice with lots of melted ice around it. There are other impacts that we have to take a look at. So one of the things is that we have seen an increase in extremes of temperature, of precipitation. But associated with that, over the last century, we've seen a decrease in the number of cold snaps. And associated with that, then when we think about the oceans, it's not just the sea level rise, but the oceans themselves are changing. So the water temperature is getting higher. The oceans are becoming more acidic as they absorb more carbon dioxide. And the oxygen content is also decreasing. And given the sensitivity of life in the ocean to having correct pH, having correct amount of oxygen, and having a correct temperature, this has potential impact to affect our global food chain. So one of the things that you might think about, and many do with regard to climate impacts, is around extreme weather events. So in this map that has information provided by the US National Oceanic and Atmospheric Administration, you see 16 events highlighted in 2017. Each of these events had more than $1 billion of impact. The total for 2017 actually exceeded $300 billion. Now, if you take a look at similar information over the last several decades, there's been over 200 such billion-dollar events in the U.S. alone, which has a total, sort of normalized value of like $1.5 trillion. And so the question is, how much is this due to normal variation? How much of this is due to impacts of climate change? And that's a fair question to ask. And what's interesting is that we're able to ascertain where some of these events are connected to climate change and some we're not certain of. So one concrete example is if we look at the wildfire season, particularly in the southwestern part of the US, it's not only is it more intense than several decades ago, the wildfire season actually is 3 months longer now than it was in, let's say, 1940. We are seeing flooding events of greater intensity. Some of this is due to storms directly, precipitation. Some of this is due to tropical events that push waters, coastal storm surge, as an example. But we also see impacts of droughts, and there's some of these have reached a crisis stage. If we look at what's happened in Iran and South Africa, and that going on right now. So one of the things that, as scientists, we really need to acknowledge, what we know and what we don't know, and in particularly the things that we don't know, or there's large uncertainty. We will want to direct our research towards those problems. And so, for example, because several of these events are severe storms, and for example, looking at tornadic events, looking at strong hailstorms, we're not certain that they're being influenced by climate change because we don't have a reliable enough record of good observations of these events. They really only go back a couple of decades. So we expect that given our ability to observe weather, record it very precisely, we'll get a clearer picture on these issues over the coming years. And another aspect is that we've been able to identify things that call them known unknowns, factors that we recognize have influence on climate, but we don't understand well enough what they may be. So as an example, what happens when the polar ice melts? Well, there's been some that have viewed some of the wide variations that we've seen in winter temperature and winter precipitation in North America and Europe this winter may be an example of that. But we're not certain that how much of that is within natural variation, but certainly the polar ice being reduced could lead to something like that. Another example is thinking about methane. So in the permafrost in the northern hemisphere, in the tundra regions, there's an enormous amount of methane that's trapped. It's frozen within the permafrost. When I say enormous, we don't know what enormous really means because there's no way of really measuring that. If the permafrost melts, and there's plenty of signatures that indicate that it may, that will release some amount of methane into the atmosphere. Now, methane is roughly 60 times more efficient as a greenhouse gas than carbon dioxide. Fortunately, it doesn't last in the atmosphere quite as long, but we don't know what will happen if that occurs. Another example of something that we know is a gap. The air and the atmosphere we breathe is not just gases. There are small particles that some may be due to pollution, some may be due to dust, sea salt, that are in the atmosphere. We don't really understand how much they interact with clouds and how that affects heating in the atmosphere. So this could be an issue where our models that predict climate may be underestimating the warming because we don't really know enough about the interaction between these aerosol particles, and clouds and how much heat that they trap from the sun. So there's for a number of these things, there are economic impacts that we can begin to quantify. In our own research at IBM, one of the things that we've been looking at is the effects on urban environments and an aspect of mitigation strategies that may be being introduced already or in plan, like, for example, making roofs green. One of the things that we want to understand is how much of that actually will reduce the impact of heat waves, and in some sense trying to tease out aspects that can be, that we can't address directly on a local scale, like warming from greenhouse gases, versus the impact of urbanization, which is something that we can do something about. But there's also a number of impacts in various industries, energy and aviation and agriculture, but there's also some health impacts that have been a subject of study in recent years. So something that's not widely known is the limits for human exposure when you're in an extremely hot and humid environment. And from a number of health studies, when a certain threshold gets exceeded, this happens to be 35 degrees Celsius by the wet bulb scale, humans can't tolerate that. And some studies have indicated that under a number of climate change scenarios, that there'll be regions of the world, like in the Middle East, parts of India, Africa, South America, where outdoor activity will be constrained because it won't be healthy for people to be outdoors. One estimate was upwards of 1 million person days per year towards the end of the century. Another example is that there's been a correlation between temperature and incidence of diabetes in the US. And the correlation is such that about 100,000 new cases would occur per year for each 1 degree Celsius increase. And then, of course, there's things that may be more widely known in the sense that if you're in an urban environment, there's a lot of there's air quality challenges. This can influence asthma, cases of asthma increasing. But now if that urban area becomes hotter, becomes more humid, pollution becomes more trapped, the increases in asthma may also be of some concern. So not to start off in sort of a rather pessimistic view, there is a lot that we can do. One place that we think is important to start is around becoming more informed. So there's a lot of information that's available, from detailed scientific studies to economic studies to just tutorials about what we know and we don't know about the atmosphere, about climate. Even our weather company group is part of IBM. They even had a digital TV series last year on the influence of climate change in each of the states of the US. And so that's something that we can do. We can become more informed, and we can help others learn more. And a lot of this is really is sort of at the core of IBM itself. So IBM has a strong tradition in environmental stewardship. It's not widely publicized. IBM tends to be kind of quiet on such matters. But we established a corporate environmental policy in 1971. So we've been doing this for years before most technology companies didn't even exist. And so part of it is about the environment in general, but there's also a strong aspect around climate change. In the last 2 decades, we as a corporation established greenhouse gas reduction strategies and specific goals. We've met and exceeded each of those goals, and we've won a number of awards for that, contributions to sustainability, and to leadership around climate change. And part of that leadership also has been an endorsement of the Paris Agreement with regard to climate change as well. So let me turn this over to Joan.
So beyond the environmental stewardship and research that IBM has been working on, another way that we've been sort of championing for environmental protection and supporting that work is through the work that we do in IBM corporate citizenship. So this is the philanthropic arm of IBM, and specifically through an initiative called World Community Grid that has been supporting basic scientific research for over a decade. My name is Juan Hindo, and I lead that initiative. Through World Community Grid, we give scientific researchers a massive amount of computing power. Each researcher gets the equivalent of their own supercomputer for free to do their work. And all of that computational power is actually donated by volunteers from all over the world. Each of them is giving up and donating whatever CPU their computer or Android device is not using and would have gone to waste otherwise. So how do we do this? We start off by partnering with research groups who are tackling really complex humanitarian problems, like looking for the next generation of clean energy materials. And each of them is using computational research techniques. So think of these as sort of a simulation or modeling tool that they're running. And these tools have become really effective and much more accurate over the last number of decades. So they've become sort of integral to the scientific process. The problem, though, is that most scientists rarely have access to enough computing power to really squeeze the most benefit out of these computational techniques and really leverage them to their fullest. Typically, scientists are having to share whatever cluster or supercomputer is available within their organization with dozens of other researchers, and they're having to scope down their work accordingly. And that's where we come in. So what we do is take what is a humongous, really large computational problem and break it up into millions of small calculations. And then we take each of these calculations and send it out to one of our volunteers who would have installed our software on their device. When that volunteer is grabbing a cup of coffee, talking on the phone, or even if they're actively using their computer, just not using all of its CPU capacity, whatever is left behind gets used to run one of these calculations on behalf of the researchers. So for the researchers that we partner with, this means that we are giving them access to 10 times, 20 times, sometimes up to 100 times more computing power than they would get their hands on otherwise. And so, yes, of course, that means that they can take their project and just scale it up 100 times bigger. But what we've seen over and over again is when you give them or sort of take out that constraint out of the equation and say, you have all the computing power that you need or want, they start to rethink the problem or the solution to the problem. They get to try out new computational techniques. They get to sort of poke at the problem from different angles, use different approaches, and frankly make discoveries that others who would have covered that challenge might not have made those discoveries otherwise. What we do ask is for them to comply with an open data policy that we have, and I'll talk a little bit more about that in a bit. And then we also, volunteer engagement is crucial. These volunteers are donating computing power, so we ask the researchers to kind of keep them up to date with what's happening on the research. And then for the volunteers that participate, they of course get to play a role in the process of scientific discovery. And they get a glimpse of what it takes to do research. The highs, the lows, the excitements, the disappointments, they get a real view of what it takes to do research. So we've been doing this for over a decade, and we've seen scientists tap into World Community Grid to help them make discoveries in everything from discovering new materials for efficient solar cells to better ways of filtering water more efficiently using nanotechnology, and a number of not just environmental problems, but also issues and challenges relating to health. And so for over a decade, we've seen firsthand the crucial role that technology plays in really pushing that research forward. So when the US pulled out of the Paris Agreement last summer, we started thinking about ways of supporting climate change and environmental researchers. And obviously it made sense at that point to start with World Community Grid. But we wanted to do more. And so for that, we partnered with 2 other groups in IBM, IBM Cloud and the Weather Company, to put together a brand new grant opportunity to provide researchers with 3 free resources: the crowdsourced computing power from World Community Grid, data storage from the IBM Cloud, and weather data from the Weather Company that Lloyd can say a bit more about.
Thank you. So the type of data that we're offering associated with this grant program is data about the past, which includes curated observations coming from public sources and coming from private sources, such as the Weather Underground, that is part of the Weather Company and IBM. And the second class of information is current weather conditions. So that also comes from sensors, but it also includes not just weather stations, it includes data from weather radars, data from spacecraft in orbit, and data from some of our own analyses of the weather conditions. And the third category is the future, essentially our weather forecasts that go out 15 days and include all the standard weather variables. Some of those data are deterministic, and some of the data are probabilistic to show relative uncertainty, particularly in the longer range weather forecasts. For all 3 of those categories, the data are provided through a consistent RESTful API, and this and it scales as well. But a key aspect of the consistency means that once you've learned to use the API, there's it's a standard method across all of those sources. So for anybody that's tried to scrape up weather data on the web or trying to find some government FTP site, that's a challenge because you have to figure out how to access, then how to parse, how to interpret the data, and that barrier sort of goes away with this. With this approach to make it easier for the researchers to use these data.
So once we bundled up these 3 resources, we put out a call for proposals. We basically asked climate change and environmental researchers to tell us how can these resources push your research forward? How can they help you do your work? And we were surprised by the response. We got more applications than I think we expected. So in just a few weeks, we got over 70 applications from research groups in over 20 different countries. And the nice thing that we saw in these proposals is that they covered many of the areas of research that Lloyd touched on, where there is currently sort of the known unknowns, the gaps in our current understanding. So I want to talk a little bit about some of the areas of research that these proposals covered. So we saw proposals that looked at ways of predicting extreme weather more accurately, proposals that looked at what does a changing climate mean to air and water quality going forward, and how does population growth impact that? How can scientists develop more sustainable farming practices so that agriculture is more resilient to a changing climate? Some of the issues that Lloyd mentioned around what impact of climate change is on asthma, other breathing conditions, and other medical conditions. We also saw proposals in the urban development space. So looking at what building code practices can have, how can that have an impact on heat generation, heat absorption, and therefore climate change. And also proposals that looked at what animal migration patterns might look like as the Earth's atmosphere changes and the climate changes as well. What we learned along the way from talking to all these research groups and getting to learn more about their work and how we can support them is that, frankly, what we were offering touches a number of their needs for technical expertise and data and technology, but it doesn't go far enough. So we'll talk a little bit about that in a bit. But we also wanted to talk about the types of proposals that can genuinely benefit from the resources that we're offering. And to start off with, I wanted to sort of give you a sense of what we look for in a proposal before we even get to sort of assess whether it's technically feasible or not. So first, we expect the research organization to be public or nonprofit. We don't make grants to commercial research entities. We also assess the scientific merit of the proposal. So we involve scientists from both within and outside of IBM who work in the same area of expertise as that proposal and ask them questions like, does this proposal address a genuine gap in our understanding of this issue? Or has this been done before? Is there a real appetite for the data that comes out of this research? Is the methodology and approach scientifically valid? We want to make sure all of that is, that we can tick that box before we proceed. I mentioned we have an open data policy, so we expect the research organizations that receive the grants to make not just the output data that gets, and the findings that get generated from the project publicly available, but also the input data and the methodologies used to generate that. And that's important for a couple of different reasons. We want other scientists to be able to recreate and regenerate that data as a way of validating it and confirming it, as well as use the output data for their own research. And this way, we're sort of spreading the benefit of the grant beyond the immediate research group that would have been the recipient of the grant. And then finally, we want to have a level of confidence that this research organization has what it takes to take this project forward from beginning to end. So we look for things like, do they have the staffing, the funding, the other resources that it takes to not just launch and run the project, but to analyze the results, to publish their findings, to comply with the open data policy. We want to have a level of confidence that they can do all of the above. Once we've done that, then we begin to look at, is the technical need that they're seeking help with a good fit for the resources that we're offering? And to give you a better sense of what it takes to run one of these projects from a technical perspective, I'll hand over to Jonathan.
Okay, so good morning, everybody. I'm Jonathan Armstrong. I work at the IBM Austin site. I'm a developer on World Community Grid. I've worked on the World Community Grid project for, about 10 years. And so one of my roles in that aspect is to perform all the integration code necessary to get a research application up and running on World Community Grid. And so to start with, I want to talk about some of those things that need to be done to make that happen. First, there's a couple of reviews that need to be done. As you can imagine, security is a big concern. So Siobhan was mentioning that we run on volunteers' machines, so they run the computations on their desktops. And you can imagine if we had any sort of security incidents, it would be a big stain on us, and we would lose a lot of trust with the volunteers. So once an application has been identified, the source code goes through a security review, and that's done by a team at IBM that deals strictly with security, and they do automated source code scans using tools like AppScan to look for security vulnerabilities. And then based on those results, they do some manual code dives to look for the concerned areas even further. And once they perform that work, they send a report back to our team, and typically on our team we'll address those issues and fix the code to close those security holes, and then we'll send those high-level findings back to the application developer so they can deal with them on their end. And then at the same time, we also do open source reviews. So a lot of the applications we run, the research organizations use either open source applications or applications that contain some open source components. And so there's some work there we got to do with IBM Legal to make sure that all of the licenses being used and all of the history of sort of the open source project, that there's no potential issues there from a legal standpoint. And once all those two reviews are passed, then begins sort of the technical work of doing all the integration code to make an application be able to run on World Community Grid. So Siobhan touched on kind of what that involves, but we use a open source platform called BOINC, which stands for the Berkeley Open Infrastructure for Network Computing. And that's sort of the standard open source platform for volunteer computing, and there's a lot of other volunteer projects that use that same thing. But in that, there's a server component that runs the back-end pieces, such as the scheduler. There's quite a large database organizing all the input-output data and the statistics and such. And there's also the web servers that not only host the website, but also control all of the flow in, all the input and downloading of input and uploading of output back to our server. So that's all running in IBM Cloud in our hosting environment. And then in addition, in the BOINC infrastructure, there's the client piece, and that's the application that the volunteers install on their machine to kind of get started working with World Community Grid. And that's important because when they're running our research applications, they run under the client, and it's important that we remain unobtrusive, so we don't want to interfere with their work. So a lot of the initial work that has to be done is to integrate to run under the BOINC client, and we have to add the necessary calls to respond to signals from BOINC to tell us to suspend. So, for example, if a volunteer's machine, if they're using it for their own local work, like maybe they're doing something very high CPU intensive or that needs a lot of resources like gaming or something, then we need to be unobtrusive and suspend, so that we have to add all the calls to handle those signals to suspend while they're doing their high CPU activity. And a big piece of the work of integrating an application to run on World Community Grid is around checkpointing. So in those cases where we have to suspend our work because the user is using their machine for their own work, we want to minimize the time lost when we restart that the research application. So we have to do things like we have to save the state of the random number generator, make sure all the objects that are important are serializable and can be written to disk, and we like to be able to save all that state to disk at least every 10 minutes or so. And so if they start to use their machine, we suspend and the process dies, and then when they come back, or when they are the load is no longer there on their machine, then we can start the process back up and continue from the last checkpoint, and we haven't lost that much CPU time. So we don't ask our volunteers to sort of change their habits. If they typically shut their machines down at night, they go ahead and shut down, and then when it starts up the next morning, it'll start from the last checkpoint and continue running. And another area where there's a lot of work done initially is the data visualization piece. So in a research application, we have to look for some of the live data running so we can get some interesting data out of there to give a visualization for the application. So from the research application, we have to find those data points and store them in shared memory. And then we write a screensaver application that reads that data, and while a computer is running a calculation, one of our calculations, it'll display an image that the volunteers will see on their screensaver. And this could typically be like molecular data, so it could be a molecule rotating on the screen. We see a lot in the instance of climate data. There may be like a map with different values shown, like the temperature and the rainfall and stuff overlaid over that map. So this is a nice piece for marketing. So if a volunteer is running a screensaver, maybe they have a friend or a coworker who says, "Oh, that's interesting. What's that?" And that's a good jumping off point to explain what World Community Grid is and how easy it is to contribute. So if we can make those visualizations as appealing as possible, that kind of helps spread the word. And so at World Community Grid, we run on several different platforms. We run on Mac, Linux, Android, and Windows. And so the application that the research organization selects is typically an HPC application, and those are usually developed and run on Unix environments and Linux environments. So there are occasions where we have to do some work to port those applications to Windows if that has not already been done, and especially with Android being a new computing environment, there's a lot of work there to port those applications to the Android platform. And then while we're doing all of this development, there's continuously standalone testing going on with the developer, so we're testing the application to make sure we don't break things as we integrate the code. But once we get the first stable release, we run alpha testing on our alpha environment, and that's a local environment to the World Community Grid team. We have a lab here in Austin, and then all the developers' machines are connected to it, where we can begin getting a wider test to get a wider array of machines to test on that might be a closer representation of the production environment. And once we have a successful alpha test, we go to beta testing, and through beta testing, we allow any of our volunteers on World Community Grid to sign up and participate in the beta program, and they'll download beta work, and we get an even wider representation of the machines on World Community Grid to test on. And once that beta test is successful, we will launch the project into production and begin running in production. And so a typical project right now runs about 100 CPU years a day on World Community Grid. So you can imagine there's a lot of input and output flowing in. So we have to write a lot of automated scripts to sort of control downloading the inputs from the researchers that they want to run, packaging those up into work units that will run on the individual volunteer's machine. And then once we get the results uploaded, we have to package those bundles up and send them to the researchers so they can begin looking at it. So there's a lot of work that goes into it, but the nice thing is we at IBM, we've got the IT part, pretty down, so we can handle all that for the researchers, and they can kind of sit back and focus on what's important to them, which is the research and all the results coming back. So that's it's a nice relationship there. And so Joanne touched on this a little bit, but initially when we're working with a research organization, they have an application that they've been running locally, and they have some hardware available where they can run simulations, but it's very limited. Even if their site has a large cluster or a supercomputer, time on those is very limited, and it can be very expensive to run on those. So they have to really focus their simulations on what can be done on their environment. And then when they come to us, we have to say, we usually, once we get a proposal, we'll send out a questionnaire, and one of the things we ask is, how much compute time do you need? And a lot of times we get answers back that we say, yeah, that's good, but that could be run in a day or in days or weeks on World Community Grid. We like to run longer simulations. So right now, our daily average is about 500 CPU years a day of research that we run on World Community Grid. And so that's where we ask them to think bigger, because as you saw on the previous slide, all of the work that has to be done to get an application to run on World Community Grid, that can take months. And it wouldn't make sense to take on that effort for something that's going to run for days or weeks. So we like projects to run for months and really years. So one of our longest running projects, 5 Days at Home, I think has run a little bit over 350,000 CPU years since the beginning, and they're still running to this day. So they've taken advantage of that. So I want to talk a little bit about what makes an application a good fit to run on World Community Grid. So we always say that we like for applications to be embarrassingly parallel, and what that means is what Joanne was saying, is that they can be chopped up into small pieces to run on an individual computer, and then we can get the results on the back end and put all those things back together. But our clients, there's no MPI communication, so there's no communication between clients. Our clients only talk to the server, download work, compute that work, and then return the results. So there's no inter-process communication. So that's what we mean by it has to be embarrassingly parallel. And then we also like to have if you think of the ratio of transfer time, the bandwidth to download the inputs to run, and then to upload the results, and then the percentage of time you want the application running the computations. You want the majority of the time to be spent with the applications running the computation, and less of the time spent on transferring the data in and out. It wouldn't make sense to if you had a large input data to transfer that. If the transfer time took longer than the actual runtime, you would just run it locally, so you wouldn't run it on World Community Grid. So that's kind of the area where we're a good fit for sort of low input, high CPU processing. And so typically on World Community Grid, in the last 30 days, we've had 250,000 different machines return a result and do computations on World Community Grid. And you can see our platforms, we're still dominated by Windows, about 58%, but Linux is kind of growing, and they're up to 38%, and then the other two are Mac and Android both share about 7% of the devices we have running on World Community Grid. And then a typical volunteer's machine is in the neighborhood of 4 to 8 CPU cores and they have 4 to 8 gigabytes of memory. So that's kind of what a typical machine is, but we have a sort of a wide range of devices. We have some people who keep their old machines running that aren't really useful for much else, but they like to keep them running just to donate time to World Community Grid. But on the other extreme, we also have volunteers who like to build machines solely to contribute to World Community Grid. So they're building high-end machines with large processors. We have, several machines that are in the neighborhood of 64 cores and lots of memory. So we kind of have both extremes. So those are the sort of applications that are a good fit for World Community Grid. But at the same time, there are some applications that maybe aren't a good fit. And for that, I'm going to turn it back over to Lloyd. And he's going to talk about some of those cases and explain a little more why they're not a good fit.
Thank you. Yeah, so the traditional modeling that's done in the environmental community, especially weather and climate, has evolved with the high-end computing for many decades. So what that meant is that as the biggest machines were built in whatever era, the first thing that was often done was to run weather or climate models. And those, one of the ways that those systems were used to sort of scale up the computations was to take the geographic area that's of interest and sort of decompose it, like taking the tiles on a floor correspond to individual areas of the Earth. And then information between those tiles has to be shared, and that's done in real time. So for example, the information inside each tile has to be shared with the tiles that surround it. And so because that's how the decomposition was done to scale the computing, the computers were built to have high bandwidth, low latency interconnects between the processors. So that's essentially the opposite of what Jonathan just described. And so, and they'll use common protocols like MPI, message passing interfaces, among the protocols used for that exchange of information. So to adapt these kinds of models to World Community Grid requires some rethinking of how do you still have to do the decomposition, but how do you share that information across the tiles? So rather than doing it in real time, we can think about the problem as a scatter-gather problem in the sense that each of the tiles could map to a single volunteer in World Community Grid, and then we do the stitching of the tiles back together as a post-process. And that allows us to think about some climate-related problems that actually can now fit on World Community Grid, where traditionally you wouldn't even think that that would be possible. So let me turn it back over to Jonathan.
Yes, so in conclusion, what we want to leave you with today is that hopefully if you're not a member of World Community Grid, you've kind of got an idea of how it works and you see how easy it is. All you have to do is go to the website worldcommunitygrid.org, sign up, download the client, install it on your computer, your Android device, and you can start running scientific research to help out the scientific community. And as Jawan mentioned, we've run projects that deal with clean energy, water, a lot of diseases such as cancer and AIDS, so a lot of good research there. And then once the winners are selected from this round of proposals for climate change, we'll begin onboarding those projects, and hopefully, sometime later this year, the first project will begin running on World Community Grid, and you can contribute to that area. In addition, some of the proposals we got, as Lloyd was mentioning, the models are changing and being adapted to run better on environments like World Community Grid. A lot of the researchers are involved with the client piece, but less with the IT piece. So if there's any developers that can help, they're looking for community models, open source projects that can kind of do the heavy lifting for the computing piece so they can focus on the climate piece. And being in Austin, other ways that you can help, being in Austin, I mean, you see electric cars everywhere. They're becoming more prevalent. These are great ways to help reduce emissions and to end our reliance on fossil fuels. And at the same time, there's all the new appliances are much more energy efficient, so replacing some of these old appliances and getting things like solar cells on your house is a great way to help. I know in Austin, it seems like every day in my neighborhood there's a new house that has solar cells up there. They're becoming much more affordable to do. But I think probably the most important thing is what Lloyd was touching on at the beginning, is that there's a lot of research out there on climate change. And just making everybody aware of what's going on and the research that's available is probably the best thing that anybody can do is spreading the word, because it's going to take everybody. This isn't going to be solved by one group alone. It's going to take everybody working together. So making everybody aware of the research and letting them go see for themselves, you know, what's going on. I think that's probably the most important piece. Yeah, so I think that's it. Thank you very much.
So if anyone would like to ask questions, there's a mic in the middle. There's any time left for questions. Walk up to the mic.
Hi, my name is Max. I'm a student at Syracuse University. I agree with you guys that spreading the spread of open source data is really important to get people informed about the effects and possible ways that climate change is affecting us. I'm wondering, you guys from IBM, if there's any technology that they are working towards that might either limit carbon emissions or reduce the effect of these carbon emissions?
Technologies that we're working on?
At IBM. Well, not you guys personally, or if it's a priority of the company to develop technology.
I mean, in the research labs, there's been work on, some of it's at a low level, like energy consumption in processors, you know, as one example, or in large-scale storage systems. Some of it's also been, because a lot of the work that we're doing is more on software and services than hardware these days. So some of it is on like some of the research that we're doing, you know, looking at more efficient decision making that has an impact. And so then you're using computing, using science, using data to help make more efficient decisions. Some of the greenhouse gas emission work that, to reduce our overall emissions, some of that actually has to do more with practices within IBM. We, at our facilities, at our labs, at our factories, and things of that sort. So it isn't so much, in that case, not developing technology, but more about development of adaptation strategies. And then those are capabilities that we do offer to the community, or we help our customers also do adaptation as well.
Thank you.
You're welcome.
Hi, this is Marcin, and I have a question about the World Community Grid. Can you, as a volunteer, decide where to donate your computing power, or are the projects being assigned randomly?
So at any one point in time, we're running multiple projects, and as a volunteer, when you sign up, you pick the causes that you want to participate in. There are different settings as well, so you can, for example, say, for now I want to sign up for these, but automatically sign me up to any new projects that come along. And then we also do a whole load of work around volunteer communications. So, when one project wraps up, we make the volunteers aware of other things that they can get involved in. But yeah, you control what you contribute to.
Thank you.
Thanks. We'll be around after the session as well. So if anyone wants to chat one-on-one, you can do that as well. Thank you.
Thank you.
Thank you.